All right, we're ready now to talk about what a basis is. I think in the end of the last video I mentioned I will also talk about dimension, but that will be in the next video after these next week. But we want to talk about basis and then how basis allows us to talk about the vector coordinate relative to a given basis. So, what is a basis? We'll go through and explain it, and then try and describe, help you see that in terms of some familiar basis that you're already familiar with. Essentially, we'll see the basis are sort of like coordinate axes that you use to identify points in the plane or in 3 space. It's the extension of that, if you will, to an arbitrary vector space. So let's see if we can make sense of it. So a vector space V, first of all, is said to be finite dimensional if there's a finite set of vectors in V that spans V. And it's called infinite dimensional if no such set exists. So you remember what we talked about when we said a set of vectors spans a vector space? What does that mean? That a set of vectors spans the vector space. It means that any vector in this vector space V can be written as a linear combination of vectors. And if it's a finite dimensional vector space, then there's a finite such set of those vectors. Okay, so we have a finite set of vectors that spans all of the vector space. If there is not, then the vector space is infinite dimensional. And we're going to be mainly dealing with finite dimensional vector spaces, but there are some infinite dimensional vector spaces, especially when we talk about some of the function vector spaces. They are infinite dimensional. So what is, first of all, a basis? Here's the definition of a basis. Given a set of n vectors in a finite dimensional vector space, so that's why we had to determine or explain what a finite dimensional vector space was. Then the set S is called a basis for the vector space V. If what? These two conditions hold. The set of vectors is linearly independent and the vectors span the space. So we've talked about just in the last videos about linear independence, and then previously we talked about spanning, and so both of these have to be true. The vectors have to be linearly independent and they must span all the space, meaning every vector in the vector space can be written as a linear combination of those vectors. Now, so first of all, what is a basis? Well, here are some standard bases. The first one I want to look at is in 3 space. All right, these 3 vectors form a basis for 3 space. Now you're familiar with these, so this is what I want you to think about. This is the vector usually called I, and this is J, and this is K. Okay? So first of all, are these 3 vectors linearly independent? Okay? Think about that. Are they linearly independent? Yes. And remember, they would be linearly dependent if what? If I could write one vector as a linear combination of the others. Is that possible? Is it possible to write the vector here, 1, 0, 0, as a linear combination of these two? Right, can you scalar multiply this vector by something, 0, 1, 0, and scalar multiply 0, 0, 1 by something, add them, and get to this vector? No, there's no way, because you're not going to get any. You can't multiply 0 by anything, right? And this first coordinate in both of these 2 vectors is 0, and I can't combine that in any way to get 1. And so you can do a similar argument for the others, right? They are clearly linearly independent. And do they span all of 3 space? Yeah. Think of any 3 space vector, right? It can be written as a linear combination of these 3 vectors, right? So the vector 3, 1, 2, 3, 1, 2 would be 3 times this vector here, plus 1 times this vector, plus 2 times this one, right? So that's what a standard basis is. Or that's what we call the standard basis for 3 space. Now there are other bases for 3 space. And why, how can we think about that? Well, let me just think about this. When you think of the basis I, J, K, you can think of the coordinate system, right? This is I is in the positive x direction, J is in the positive y direction, K is in the positive z direction. And so it's like an axis. And there's times when you want to scale your axes. You know, think about if you are looking at, I don't know, the height of some, like a space, a rocket or something you're launching into space. And you have on the horizontal axis the time, elapsed time or something, and then the vertical axis is the height. Okay, so how would you, so in the x direction you could be talking about the 1, 0, the I vector, and in the y direction you could talk about 0, 1, j. Well, when you do an axis, you have little tick marks, right, that show you the units, like you might have 10 feet, 20 feet, 30 feet, and so on, right, 10 units apart. Okay, if you're modeling the height of a rocket going into space, do you think that's a good scale to use? Time in minutes, for instance, and then the height, 10 feet, 20 feet, 30 feet, 40 feet, would that be a good scale to use? Probably not if you're going to go into space, right? You probably want to keep a scale that's much bigger, like instead of increments of 10 feet, you might want to do increments of 10,000 feet or 100,000 feet, I don't know, right? So that you can see clearly what the path of the rocket is as time progresses. So scaling your axis is a way that we can essentially change basis, if you think about it that way. Or, you've probably seen those problems in physics maybe where you have a ramp, right? And you've got an object on the ramp and you're kind of pushing the object up the ramp or something, and you're trying to resolve the forces. Well, it may be that you want to use, and it's typical, right, to use the x and y direction for the weight and everything, but there are times when you might want to do the components of the forces along this direction. And in that case, your axis might be skewed. Instead of the x and y axis, you might use this line on top of the ruler as one axis. So you can have sort of a skewed coordinate system or axis system, if you will. So bottom line is that if you think about those different types of axes that we can have in 2 and 3 space, that's the idea of a basis. Now when we extend it to other spaces like n space, here is the standard basis in n space. You can see it's just a natural extension of the basis that we have in 3 space. There's n vectors here. This is the standard basis again, and there are actually many bases we can come up with for n space, but this is what we call the standard basis, and it'll make sense later on why we call that the standard basis. What about p sub n? What's that? That's a set of all polynomials of degree n or less, right? Think about this. This is a basis. This is what we call the standard basis. Every polynomial of degree n or less can be written as a linear combination of these vectors, right? And of course these vectors are just polynomials, right, in this case. So that's pretty clear, right? I can just add scalar multiples of these quantities to create a polynomial of degree n or less. And are they linearly independent? Are these vectors here linearly independent? Definitely, right? Can I write 1 in terms of these others? No. Right? Can I write x in terms of the other ones? No. Right? These are all not like terms. Right? Each one of these polynomials is not a like term. Right? They all have x to different powers, so I can't combine them by adding in any way to create the others. M22, and we actually came up with this basis a few lectures ago. We showed that these vectors spanned all of M22. Okay, so they certainly span all of M22, which again is the set of all 2 by 2 matrices. Are these 4 matrices linearly independent? Well, let me ask you, can you write this matrix here as a linear combination of these 3 guys? Can I add these 3 guys in some combination to get to this one? No way, right? Because it's got a 0. Each of them have a 0 in that first row, first column entry. There's no way I'm going to get that to sum to 1. Okay, so these are linearly independent. Okay, and so these are the standard basis, and that's what you want to think of when you're thinking of basis. But there's other basis. So let's talk about 3 space. That we're pretty familiar with I, J, and K as being a basis. How would we determine if something a set of vectors forms a basis for 3 space. Okay, well, let's see what we would do. The definition said what? A basis has to have what 2 things? These vectors must be what? Number 1, linearly independent, and number 2, they have to span the space. So let's answer both these questions. Let's look at the first one. Are these vectors linearly independent? Okay. Well, what do we do there? This was what we talked about in the last videos, right? Last set of videos. We take a linear combination of these vectors and we set it equal to what? We set it equal to the 0 vector, which in 3 space is the vector 0, 0, 0, right? Okay. Now, we've done this several times in those last videos, and so I want you to be able to understand how to get this, but I'm going to let you do that. This yields a system of 3 equations in 3 unknowns. And the system is the system AX equals 0. Right? X is the unknowns, right? The unknowns are what? K1, K2, and K3. And what's A? It's the coefficients. And I think we've seen this enough to know how to construct this coefficient matrix. If you don't, please contact me, ask me during one of our Zoom sessions, or send me an email. But this is the coefficient matrix. Again, if you don't understand how to get this A, go back and look at the previous videos on linear independence. Okay, so this is the coefficient matrix. So how can I determine, what am I looking for? If I'm looking for linear independence, I'm looking to see what? Does this system have what? Only the trivial solution. If it has only the trivial solution, then this set of vectors is linearly independent. And so notice this is a system of 3 equations and 3 unknowns, which means our coefficient matrix is square. So we can use the equivalent statements to an invertible matrix here. If I take the determinant of A, I'll let you do that with your calculator. You'll get 3, right? Which is clearly not equal to 0. And therefore, what do we know? A is invertible, and AX equals 0 has only the trivial solution. And therefore, what do we know? Linearly independent? Yes. 1 down, 1 to go. We have to have what 2 things again for a basis? Linearly independent, and what? The vectors must span the space. So the question is, do they span the vector space? What's the vector space? It's 3 space, right? Do they span 3 space, right? Well, what are we looking at here then? Well, here we say we have an arbitrary vector B in 3 space. Okay, so let's say B is arbitrary. So what would its coordinates be? I don't know, and I don't know, right? But 3 possibly distinct and different values. So any one, right? Pick any B. And the question is, do there exist scalars? And we'll just call them K1, K2, K3, such that what? K1 times our first vector, and it's going to look very similar to this, isn't it, right? K1 times our first vector plus K2 times our second vector times K3 times our third vector. It's very similar to what we have above. Equals what? Equals B, right? Equals B, which is B1, B2, B3. Right? Well, this yields a system of, again, 3 equations and 3 unknowns, which is AX equal B. Okay? And this A is the same as the A above, right? From this part right here, we're going to construct the A. Remember, X again is our unknowns, K1, K2, K3, and of course our column vector B here is B1, B2, B3. Okay, so what's the question? Do there exist scalars? Right? Is this equation always have a solution for no matter what these values are here, no matter what b1, b2, and b3 are? That's the question, which translates into what? Is this system what? Consistent? Does it have a solution for every such b? That sounds familiar. Again, A is 3 by 3. This is consistent. This system is consistent if what? If and only if, let's say, is consistent for every 3 by 1 matrix B. Right? All that. If and only if what? If and only if A is invertible. Which is true if and only if what? The determinant of A is not equal to 0. Right? So if the determinant of A is not equal to 0, A is invertible, and this system is always consistent. And we know how to solve the system. We've talked about that, and we'll talk about that some more. But, right? That tells me what? We span the space. Well, how do I know the determinant of A is not equal to 0? I guess I should say it's the same one, right, which we computed up here. The determinant of A was 3, and so that information, together with that, tells me, yes, we span space. So we're linearly independent, and we span the space. And so what's our answer up here? Does this set form a basis? Yes. Right? We can answer that now definitively because we've shown the two things that we're required to show, linear independence, and they span the space. Now, some of you might say, hey, wait a minute. When we determined linear independence, we did all this work, but the bottom line was what? Was this determinant not equal to 0? If it was not equal to 0, then we're linearly independent. Okay? And we said span 3 space. We did all this work, and we said what? Well, we'll span if and only if what? The system is consistent for every such b, and that's true if and only if what? The determinant of A is what? Not equal to 0. The same deciding thing is what? If the determinant of A is not equal to 0. Of course, this only works if we're in a situation where we have what? Coefficient matrix being square. And so if we have the same number of unknowns as we do equations. And in that case, you'll see we kind of kill 2 birds with 1 stone. I don't know if you know that saying, but we accomplish 2 tasks with 1 thing. And this will be important. We'll state this in a theorem later on that will say under certain conditions to determine if we have a basis, we actually only have to check one of the 2 conditions because then the other one will automatically follow. But we have to do a little bit more before we state that theorem, and so we'll get to it. But that's the way we could show right now whether or not we have a basis. Important thing to remember, basis has 2 requirements, linear independence, and they span the space. Let's do another example. Does this set of vectors, which in this case vectors are what? Polynomials. Do they form a basis for P sub 2? Remember, P sub 2 is what? A set of all polynomials of what? Degree 2 or less. P sub 2 is the set of all polynomials of degree 2 or less. Okay. So, do we have a basis? Well, you know, what are we going to start with? Linear independence or spanning the space? I think it's easier always to go with linear independence. Let's check that first. Are we linearly independent, right? So what are we going to say? You know, k1 times the first polynomial, which is x squared plus 1, plus k2 times negative x plus 2, plus k3 times x squared plus x minus 1. Does that equal the 0 vector, right? Of course, the 0 vector in this case is what? 0x squared plus 0x plus 0. That's our 0 polynomial, if you will. Okay. So, again, you should be able to, from this, deduce the system of linear equations. We did an example of linear independence with polynomials before. And basically, you're going to equate what? All the coefficients of x squared over here. So you'll have k1 plus k3. That's going to be the coefficient of x squared over here, right? k1 plus k3. That's going to have to equal 0. And then what? You're going to have your x terms, negative k2x and what? Plus k3x. So we're going to have negative k2 plus k3 has to equal what? The coefficient of x, which is 0. And then our constant terms, k1 plus 2k2 minus k3 has to equal 0. Right? And so we have 3 equations. Oh, wait a minute. I'm sorry. I forgot one of my polynomials. I'm not in class, so no one is here to correct me. I missed that guy, didn't I? I'm sorry. And I even have notes over here as to what I'm supposed to do. So may I insert in here, I'm sorry, may I insert in here plus k4, I know it's out of order, sorry, but again, it doesn't matter the order that these are in, 3x2 plus 3x. I am sorry. You're probably going, what in the world is he doing? Okay, sorry, I forgot that one. Okay, but again, so I've got, for x squared, I've got k1x squared plus 3k4 x squared plus k3x squared, sorry. Okay, and they're all, the coefficients of x squared will be equal to 0. So notice I've got, for the x squared terms, I'll get an equation. For the x terms, I'll get an equation. And for the constant terms, I'll get an equation. So I'm going to get a system. And it's a system of homogeneous equations. Why do I say homogeneous? What in the world does that mean again? Constants are all what? 0, right? Homogeneous equations. Linear, of course. With 3 equations, right? And how many unknowns? How many unknowns? K1, K2, K3, and I forgot almost. K4, right? I need 4 of those unknowns, right? Because I had 4 polynomials in here. And 4 unknowns. I have more unknowns than equations. Do you remember a theorem we proved at the end of the last lecture on linear independence? I hope you do. We have more unknowns than equations. And for a homogeneous system, what does that mean? More unknowns than equations, what's that mean? That means, again, the system is always consistent, right? But if we have more equations than unknowns, there's going to be at least one of our unknowns that will not have a leading one. Think about it, right? Our coefficient matrix, right? When we come up with the AX equals 0, right? It's going to be what size matrix? 3 equations. So how many rows will matrix A have? 3 rows. How many columns? 4 unknowns, 4 columns, right? 1 for each unknown. So you're going to have 3 rows, 4 columns. What's the most number of leading ones you can have with 3 rows and 4 columns? You say, I can have 4 leading ones because I got 1 in each column. Well, no, you can't because you only have 3 rows. Do you see that? The most you can have is 3. Right? You can have 1 leading one in each row. That means there's 1 column without a leading one, meaning that one variable will be a free variable, which becomes a parameter. So we know we have infinitely many solutions. And what does it mean if we have infinitely many solutions when we're talking about linear independence? What's it mean? It means they are not linearly independent. Those vectors are linearly dependent. Because again, they're linearly independent if and only if what? The only solution for this equation is when all the k1, k2, k3, and k4 are what? Equal to 0. And so therefore, the polynomials are linearly independent. Sorry, linearly dependent. Did I say independent? Linearly dependent. And so this is a no, not linear independent. But more importantly, right, since we've determined the polynomials are linearly independent, what can we say to the original question? Do these vectors form a basis for a piece of 2? Remember, a basis, the vectors have to be linearly independent. Well, here they're linearly dependent. And so the answer is no, right? Because this situation, right, polynomials are linearly dependent. Now, do we need to check the other condition? Do they span the space? No, I mean, there's no need to. We've already deduced that they're not going to be a basis. So we can stop there. Okay. All right. Let's stop this video, and in the next one we're going to take a look at a theorem that shows how the importance of a basis, basically, and that is to talk about the coordinates relative to a given basis for any vector. So we're going to talk about that in the next video.